Welcome to this piece. This will be my last lecture. From tomorrow onwards, one of my colleagues will take over, Professor Bharat Seth. So I'll just recapture what we had done in the last class lecture. We had looked at servo motors, particularly the PM, permanent magnet motors. Okay, this is what we had seen last class. We had looked at their capabilities, then we had also seen how to select them. We had gone up to the point of selecting the motor. The next step is to select the electronics. Now this is the electronics, okay, the power side, how to select it. We will briefly look at that before we pass on to stepper motors. Okay. Now the drive electronics, which are used for drive electronics. There are other electronics for the feedback control and all that, but we are only examining the drive electronics for the servo motor. Now yesterday I had shown you how to calculate the various torques, the continuous, the RMS value and the peak value. All this we had looked at. We had seen various segments of the motion, incremental motion, the acceleration segment, the deceleration segment, the uniform velocity segment, all this, and individually we had calculated the torques as T1, T2, T3 and T4. Yesterday we had done that, and based on that we had selected the motor, the previous class. Now what we have to do is, for each of these periods T1, T4, T1, T2, T3 and T4 are the torques in each of these period segments. T1 is for the acceleration, the motor picks up speed, T2 is for the uniform velocity, where most of the time you are overcoming the what you call friction load, unless there is another external load. T3 is the deceleration phase, where you need certain torque, and T4 is, of course, the torque was 0 in our case, the example we had taken. Now for each of these we will have to calculate the current and voltage. Remember, current will depend on the torque and voltage will depend on the current and voltage. For each of these segments we have to calculate. Okay, the current I is given by the torque divided by what is known as a torque constant of the motor, KT, K suffix T, the torque constant. Calculate for each of these segments. You know the torque, you use KT, which is usually a constant for a given motor. Which is, why should I say usually? It's a constant for a given motor. Use that to calculate what is the current required, and make sure the electronics will sustain that current. You have the peak current, you have the continuous current. The electronics must be able to, many electronic devices will be able to give something more than what they are designed for a very brief period. So you have to look up. You have the peak current as well as the continuous current, RMS current. Look at both. Go to the catalog which gives you the drives, and then make sure that it satisfies your requirements. This is how the electronics is selected. Okay. Now for the voltage, it should also supply the requisite voltage, because speed depends on the voltage. You are moving the motor over a wide range of speeds. As you accelerate, maintain a uniform velocity and go down, so you require differing voltages during various phases. Okay. So for that you have to make sure that your voltage is also adequate. So the voltage is calculated as Ri plus Ke, okay, where Ke is the electrical constant and R is the motor resistance. There is going to be a voltage drop because of the resistance, so that you have to take into account depending on the current flowing through. So for each of these segments you calculate this. For the RMS value also you calculate the voltage. You know the torques, individual segments, you know the RMS torque, you know the resistance of the motor which is given in the catalog by the motor manufacturer, then you can calculate this term and then add to it KE is given by the manufacturer into the motor speed. You take the maximum speed of the motor and add it up, sum it up. Omega m is the speed of the motor. The electrical constant KE is given by the manufacturer. Okay? So you will know the voltage, maximum voltage required. Using these two, you select the drive electronics. Okay? If the requisite electronics is not available, okay, you may have to revise your motor design, or you may have to look for another compatible. Usually most motor manufacturers give the electronics also along with that. It makes sense to buy both from the same party. So this is how the drive electronics are selected for a servo motor. Now the reason why I have gone through the servo motor is that's one which you are going to frequently encounter as you look into the area of robotics. Okay. Now after you have done all this, there are certain things which you have to do which I have not mentioned here. If you go to any motor manufacturer or any standard textbook on servo drives, you will see that heating is a very important consideration. That is a very important consideration. Heating up of the motor. If your selection of the drive is not careful, the electronics or the motor is not done properly, you are not careful, you might end up having a motor which tends to heat up. When it heats up, as you know, most of these permanent magnets or any motors, heating is causes damage, excessive heating. In a PM motor, because of rare earth magnets, they are not very good conductors of heat. So if any heat is there, and the cycling of the heat may lead to the magnet losing its magnetic properties. So that's why heating one has to address carefully. You will find that almost all motor manufacturers will give you curves by which you can determine what is the rise in temperature given an ambient temperature, or they may provide you small formulae which you could use to look at heating. So heating is a very important thing. Heating. Check. Remember, the ambient temperature matters in this case. Temperature. If you are operating very close to some furnaces and all, you will have to worry about the ambient temperature. You may have to provide some fans, or motors come with and without those blowers which will blow air through the motor in order to cool it. So your selection will depend on that. You may have to select a motor with a blower in case the heating is excessive. I am talking of incremental motion. That's what we are going to encounter in robotics. The arm moves, accelerates, moves at a constant velocity, decelerates, then waits, and then keeps on moving. That's where the difficulties come. In continuous motion, if a motor is rotating continuously, it will attain some steady state. It's fairly straightforward to estimate all these things. The drive electronics, the motor ratings, heating, all these are fairly straightforward. But when it is doing this incremental motion, one has to be pretty careful. There are some other things which I would like to, based on the experience we have had, I would like to touch upon in the motor selection. See, motors typically are called upon to drive a load through there is a motor shaft, and there might be either a belt or a gear connecting it to the load. So let's see here. Here is a belt. I am showing a belt, drive. This is the motor. Then there is the motor shaft inside. Okay. Through a belt drive, it is driving a load. The load is here. LO. This is the load. It is driving the load. As you are all aware, the belt will exert a tension T1 plus T2, where T1 is the tight side or T2 is the slack side tension. There will be a tension in the belt which will tend to pull these two pulleys together, belt pulleys. In gears also, there is going to be a radial force in gear pairs also. Remember that. Now that will end up loading the motor bearings or gearbox. It depends on whether you have directly using a motor or you have a gearbox also attached. Okay, it will end up loading these two. Now you have purchased the motor, so you have to make sure that these bearings can take up this. That is something which you have to make sure. Many a time you may have to ask the what you call that manufacturer that you have such a particular load on it, the tension of the belt, can the bearings take it up? You can easily estimate the reaction on the bearings. If this is R2 and the bearing here, sorry, this is one bearing, this is the second bearing, there might be R1 and there is a load here. Load on shaft. You can estimate this from simple mechanics by equating, by looking at the moments and the forces, equilibrium. You can estimate the reactions and go to him and ask him whether this particular bearing will withstand that, and the life of the bearing. You have to work out the life rate at which you are working on, basing it on some average speed. You have to work out what will be the life of the bearing. Most motor manufacturers will give you this data, but many a time the normal catalogs do not contain it. You may have to go back to the manufacturer and ask about this. This one more check we have to make sure, the bearings, that they can withstand. Many, I have seen many designers, ignoring this and paying a lot for it, because the whole motor is damaged virtually once the bearings are damaged. Another thing you have to look at is natural frequencies. There is a natural frequency, the drive system from the motor to the load, lot of stiffnesses involved, torsional stiffness and so many things. Root K by M is the natural frequency of any system. In case of a torsional system, you will have to replace this by I, right, the moment of inertia. So you know the individual system natural frequencies in the transmission line. You make sure that the motor, these, you operate away from these natural frequencies, but if you have to go through those natural frequencies, you will have to provide a damper. Many a time that will happen. Typically the natural frequencies in these drives, okay, natural frequencies of the various drive elements, systems, will be usually of the order of say about 10 to 20 hertz. 10 to 20 hertz. That is, okay, cycles per second, 10 to 20 hertz, the natural frequencies. One can estimate those natural frequencies of various segments of the transmission system and see whether the motor can be kept away, the forcing frequency can be kept away, or if you have to pass through the natural frequency to attain, you have to make sure there are dampers, otherwise vibration will set in, resonance will set in. So these are some of the things which one should examine as he uses these motors, okay, and the associated. So we have now more or less seen the various what you call servos, their capabilities and how to select them, and verifying whether your design is okay. These are the steps we had seen as far as servo motors are concerned. Permanent magnet, there are many other types of servo motors, AC servo motors. We are not touching upon them because there is not enough time for this in this course. But this background will help you look at those also. If you open a book or any textbook, there is another drive which is frequently used, the stepper motor. Here, as I had told you long back, perhaps the sequence of pulses to the motor turns it through 1 degree. Let us see how the stepper motor functions, because that is what will give us a feel of what is going on. Essentially what it contains is a rotor and a stator like any motor. Now mind you, all these have now started coming out in the linear drives also. That means No longer are these stepper motors and servo motors just those which rotate, where the shaft rotates, but you can also have a translating stage driven by these things. That design of that is more or less along similar, selection of those also is along similar lines. So we won't touch that. Now in the case of the stepper motor, the rotor, there are two types of course, the motors. There is what is known as a variable reluctance motor, and another is a permanent magnet motor. Okay, many of you might be. In the variable reluctance motor, we have a soft steel rotor. Okay, soft steel rotor. The rotor tends to be light, whereas in the permanent magnet stepper motor, you have permanent magnets as a rotor. I will just touch upon the permanent magnet stepper motor, PM stepper motor. Now there are many more things about stepper motors, which I am not going to discuss, because you can always look up a book. And then variable reluctance, I just touch upon some important aspects. Variable reluctance is the other one. Okay. Now let us look at this permanent magnet stepper motor. I have got a rotor which on one side has got a south pole, another side a north. Is the rotor. Then I have got a stator here of 4 coils. These are the coils. I will show them outside. 1, 2, disposed 90 degrees apart. These are the 4 coils. But this could be either north or south, depending on how you the current, how you push in the current, north or south. Similarly, this also could be north or south. This also could be north or south. Remember, mind you, this is a permanent magnet rotor. So this is a rotor. 2 halves, one side, I mean not 2 halves, I mean one side is south, one side is north. Now let us assemble these two and see what happens. Now I have got south here, I have got north here. Okay, I have these 4 magnets surrounding this. Initially, this is north, this is north, this is south, and this is south, and the rotor position is given by this arrow. That's the reference position. So I am not showing the entire circle of the stator. I am just showing these 4. Okay, north, south, north, south. Then what you do is you switch these so that this becomes south and this becomes north, and this is still north, this is still south. It's a very simple way of understanding stepper motors. That's it. This is south, this is north. You switch. This was originally north south, now it has become south north. Then what will happen is this rotor will start rotating. The rotor will start rotating. That arrow, it will start rotating. Okay, and it will occupy this position. It will occupy. This has become north. See, the rotor has rotated 90 degrees. It will occupy this position. This is north, this is south, this is north. It has turned from here to, the moment I have switched from north to south, I have switched it to south and north. This way, the rotor will rotate. I think you can visualize. You see the poles. This repulses, this attracts. Now it has moved through 90 degrees, right? Halfway through, see what happens is, as I switch, now again I switch again once more in order to further move it. This is north, this is south. I now switch it so that now I will show you this picture. When I see, okay, currently at this point it is south, here this is north. I think the letters are not large, but you will have to, it's here. Now when I switch it here, north, south, south, north, again compare, these two have been switched. The rotor now occupies this position, where this is north and this is south. This is south. From here it has come out. So every time I switch these magnets, electric coils, the rotor keeps rotating. Okay. Now the torque output of the rotor is going to fluctuate as it moves between these magnets. So you will not get a, you will get a torque varying like this. And the minimum push or minimum torque is obtained when it is in between two positions. See, it is starting here, it is ending here, somewhere in the 45 degrees in between, you get the minimum torque. That is the running torque. There is a huge push here. Towards the end also, there is enough of force available, but in the middle, that is the lowest position where, see, if this is a 90 degree one, the one I have shown, in the middle you get the lowest torque. That is the one that governs how much torque the motor can deliver. That is known as the running torque. That is known as the running torque. Okay, in between the two positions, in between one step, in the midway through the step, that is where the torque obtained is a minimum, and that is the one that governs how much torque the motor can provide. That is known as the running torque. Okay. At the initial point, at the start, it has sufficient torque, large torque. At the end also it has large torque available, but in the middle you will find that the torque drops slightly. Okay, is that clear? Between the two magnets somewhere. Is it clear? Okay. Now this is step 0. It has come to step 1 and then it has come to step 2. One step from here to here and another step from here to here. Which one? We will come to that. It can sometimes it can stop in the middle. Where is the lowest torque point? If your friction is very large, when it comes to the lowest torque point, it may not go beyond that. Okay. Now, typical step sizes available in standard motors is 0.9, 1.8 degrees. Then you can go to 7.5 degrees, 15 degrees, 30 degrees and so on. These are the step angles. They are called the step angles. If the friction. There is one more thing with the stepper motor which you should know. What is known as the holding torque. If you energize the stepper motor, the shaft does not rotate, but it can hold on to a particular load. It is, one could show it like this. The stepper, if this is the stepper motor shaft, on that you put a arm, hang a weight, energize the motor will hold the holding torque is the torque at which the motor can continue to hold it. Any more weight you put, the torque increases, it will not be able to hold it. That is known as the holding torque. Should know this holding torque, because if you want to hold the robot arm up and you want to keep it there, keeping the motor energized, it will hold the arm there. What is known as the holding torque. Okay. So this is also given by the motor manufacturer. He gives you what is the holding torque of that stepper motor. Now we come to the performance of the stepper motor, the performance characteristics. Okay, if I plot torque versus speed, I get two curves. sorry, this should be outside. This intermediate position, this one, is slightly, okay, let me see, I can get it right, yeah. This intermediate area is called the slew range. SLEW RA. This darkened area which I have darkened with dots, the whole thing, whole of this, including this, is called the slew range. This is the torque versus speed. Notice that the speed is on the x-axis and torque is on the y-axis. It's not the way we did it for the servo motor. This is known as the slew range. Okay. Now let us go back to the stepper motor. You are giving it a series of pulses in order to make it step. Okay. You are switching these coils, giving it a series of pulses. The moment you switch, because of the inductance of the coils, okay, the inductance of the coils plays a significant role in the torque availability. At slower switching rates, that is at slower speeds, the inductance doesn't have much of an effect on the torque. But as you increase the speed, you are switching at a very fast rate. The current in the coil will not rise. Essentially the switching is a square pulse. But because of inductance, it will no longer require. There is a rise time, there is a fall time. Okay. At the slower speeds, this particular phenomena doesn't have much effect on the torque capability of the motor, available torque. But as the speeds increase, you are switching at a faster rate, the inductance starts playing a role, and the torque available decreases. Okay, the torque available decreases as you increase the speed. Okay, all right, is that okay? Now let's see what happens. What is the meaning of all this? How does it affect us? I just darken this a little more, the slew range. In the slew range, where the switching is higher, as you can see, I have increased as the speed is increasing. In the slew range, where the switching is higher, the torque is poor. Consequently, you can only overcome the friction torque. It cannot accelerate and decelerate with ease in this. See, once the motor has picked up speed and you have come to this zone, you have crossed this line, this boundary you have crossed and come to this, should not expect the motor to be accelerated and decelerated at very large rates, because the torque available is very low. And a consequence of this is that the motor will, if you try to attempt to either accelerate or decelerate it at a very high rate, when I am saying very fast rate, then the motor will slip. It will miss some of the steps in this zone, in the slew range. Okay, you got it? When the motor is moving at a very high speed, you are giving it a sequence of pulses. Now you want to increase the speed. If you suddenly try to increase, accelerate it, motor will miss steps when it is operating here. There is no such problem here below the. So that means you try to operate, acceleration and deceleration should be done within this. Okay, when you enter the slew range, operating speeds enter the slew range, don't try to accelerate or decelerate. Now this is something which most novice, I have seen novice students do not look at this torque and slew range, the torque speed curve and the slew range, they do not look at. So there is what is known as a pull-in torque. For starting the motor. That means, supposing you have a motor and a load, okay, you want to, supposing you have a specific torque here. Now, as long as your speed is, see, I have the torque, this is one point, I draw a horizontal line, I come up to this. Okay. This is the maximum speed within which you can safely accelerate and decelerate. This is the pull-in torque. Given a torque load, this is the maximum speed. If you look at the speed, start from the speed, if you have this speed, operating speed is here, you want to, then if the torque is above this, you will not be able to accelerate it comfortably. If the torque is below this, you will be able to accelerate it comfortably. Load torque. If the load torque is below this, you will be able to accelerate it comfortably. Now you have accelerated, let us say you have entered this zone. Don't try to accelerate or decelerate. This outer boundary will determine what is known as the pull-out torque. Supposing I have got a torque here, load torque, and corresponding to this, if I try to go beyond this speed, the motor will start losing steps. Until this speed, it will be in synchronization. If I try to go beyond this, I am crossing this boundary coming out. Mind you, the load torque is here. So I am crossing this boundary and coming out. If I try to go beyond this speed, I have drawn this. Any point beyond this speed, the motor will start losing steps. So these are the points you have to bear in mind when you select a stepper motor for your drives. Okay. Now regarding calculating the size of the stepper and all, procedures are similar to what we had seen in the servo motor. Okay. Procedures are similar. Only thing you have to remember is that you have to carefully operate the stepper. If you violate these, you will lose steps. That's what it is. Okay. Now that to go into the slew range and out, you have to accelerate very slowly or decelerate very slowly. Another thing. So let us look at it again. Given a torque load, there is a maximum speed beyond which you cannot comfortably accelerate or decelerate. Okay? This is the speed. Given a torque, okay, and if you are moving at a constant beyond a particular level speed, it will start in this zone, it will be in synchronized with the switching, it will be following the switching, it will follow the switching without losing steps. Beyond a particular speed, it will start losing steps. So these are things which are. So this is the acceleration deceleration zone. Here, if you are careful, your motor will not miss steps. If you are not careful but cross this boundary, you ask for more speed than what you, then the motor will start missing steps. These are the 2 points you have to remember. Designing servo motors. Okay. There are many other servos like the micro servo and all that. I'm sorry, designing stepper motors. There are many other like the micro steppers and all that. I will leave it to you to have a look at it, what those micro steppers are. They have become quite popular. They are being used for various. So this by and large completes my way we have looked at the electrical actuators. You know, in this course we are only going to give you some flavor of all these actuators. We are not going to go into depth of these actuators because each of these constitutes a separate course by itself. Servo motor design and servo motor control and all this, full course can be taught on that. Likewise, in stepper motors also there are full books which will give you details. But you should just know what are the basics. Now let us look at the hydraulic and pneumatic systems. We will just look at hydraulic and pneumatic actuators. Here also I will just touch upon some things which will allow you to do some reading on your own as you go ahead. A typical hydraulic system, I will talk interchangeably of both hydraulics and pneumatics, because many things are similar here in both. It consists of a pump and a tank of oil called a sump. This is the sump where oil is contained. Then it takes in oil, feeds it to the system which you want. The system is sitting here. There is a system of cylinders which you want to power. System of cylinders. System of cylinders. The pump takes in oil from the sump and pumps it up. There might be filters on the way in order to filter the oil. These are very sensitive to dust, particularly the servo hydraulics are very sensitive to dust. There are very fine pores through which, fine holes through which the oil flows, and they are very sensitive to dust. So you must have proper filters. Also you must remove moisture if there is any in the oil. Air should not be entrapped. Air should not be entrapped in the oil. So when you start your system, it takes quite some time to fill it up with oil and make sure that there is no entrapped air, entrapped moisture. Oil will deteriorate when there is moisture. So you have to make sure of all these things when you. Then there is what is known as a non-return valve. This is a typical non-return valve. Then there is a pressure release valve, a safety valve. Sometimes for some reason if the pressure in the system goes up, the valve will release the oil, usually back to the sump. Remember that. You can't throw the oil all over the shop floor. It goes back to the sump. Then there is what is known as an accumulator. In all these systems, pressure fluctuates. This accumulator is a very simple device. Essentially, you have a tank. I will put it on top with a gas bag in it. You can do one thing. One simple accumulator would be to have oil flowing like this, okay, through a piston and cylinder, keeping a weight on top. This could be a simple accumulator. Oil flowing out. Whenever the system pressure comes down, goes up, this weight is pushed up. When the system pressure goes down, downstream, the weight comes down and maintains the same pressure. That's what is you must have heard of accumulators in several instances. That's what the accumulator is for. Instead of this, they now have this gas bag inside, and the oil is around. There is a bag of gas. If the pressure increases, the gas bag is squeezed, and from the inlet side, if the pressure decreases, the squeezed gas bag expands and maintains the same pressure on the line. That is all. Instead of the weight, you will find this in all this. A simple device which has been the accumulator. Then it goes to the system of cylinders which you want to control. From here, this system, there is a return to the sump. There are several types of pumps: rotary, and reciprocating. Positive drives, rotary and reciprocating positive drives. There is a very interesting pump called the swash plate, based on the swash plate. I think you should look up this particular. It's a variable displacement pump. You can vary the displacement, vary the stroke. Variable displacement. I leave it to you to see it. It's a very interesting mechanism. Variable displacement. See, you can control flow by having a valve on the line, or you can vary the pump stroke, number of strokes or whatever it is, in order to control the flow. That also you can. It's a variable displacement. Okay. These are the various pumps which are used in. In the case of pneumatics, you will end up with a compressor and a compressed line. There also you will have filters, you have dehumidifiers, dryers. You would like the air to be dry. There are two ways of drying. You pass it through some silica gel, something like that, or you. Another way of drying nowadays, which has become very popular, is a refrigeration system through which the air is passed. It sucks off the moisture. It condenses the moisture and takes it out. We have it in one of our labs. They're very compact. Because the moisture in the air will condense somewhere and create problems in a pneumatic system. You don't want a moist air going through the system, particularly in places like Mumbai, where there is a lot of moisture. This becomes quite important. You need dry air. Dry air systems, you either pass it through some gel, silica gel or something like that, or you have a low temperature system where the moisture condenses and is extracted. This is what is done in air conditioners. In air conditioners, there are dehumidifiers which are commercially available. That is as far as the pneumatics is concerned. In hydraulics also, you have to make sure there is no moisture to begin with in the oil. Because moisture, in the presence of moisture, oil starts deteriorating very fast. There is one more point here which, as soon as oil is circulating, doing work, high pressure, low pressure, it tends to heat up. So there is always a heat, oil cooler which is inserted into the sump. There is an oil cooler. When an oil is working in a closed loop, inside a closed loop it is circulating, it tends to heat up. So, the pump is putting in some energy and it tends to heat up. There will be friction in the cylinders, that will generate some heat. The oil will tend to heat up. That heat has to be extracted. So there is an oil cooler in the sump. Many a time it is in the sump. Sometimes you may have to put it on one of the lines in order to extract the oil, so that the oil temperature is maintained. Otherwise, the performance of the system will keep changing. So these are some of the elements of a pneumatic and hydraulic system. Typically, the pneumatic and hydraulic system drive what are known as cylinders. There are two types of cylinders. There are two types. One is single acting, another is double acting. Single acting and double acting. I am referring to the reciprocating type of cylinders. So a single acting cylinder is, the name looks formidable, but actually it is a very simple device. When you admit oil or air onto this side of the piston moves, compressing the spring, and the return motion is by the spring. That's why it's called single acting. In one direction, the oil or pneumatic, the hydraulic or pneumatic pressure acts when the motion is in one direction. The return motion is through a spring. Sometimes they call them spring return and all that, but this is known as a single acting cylinder. When you are admitting oil to both sides for the motion, oil or air to both sides, you have what is known as the double acting. These are some of the terminologies which you should be familiar with. Double acting. You have to admit oil on this side to push it this way. You have to admit oil onto this side to This is known as a double acting cylinder. Obviously, supposing you are calculating how much is there is a particular amount of pressure you have, oil pressure you have, you would like to know how much is the load available, the load torque it can, the force available. So you will multiply the pressure by the area of the piston. But on this side, remember, the piston rod is sitting there, so area is cut down. See, this area minus this area, this has to be kept in mind in a double acting system. Okay, it has to be kept in mind. On one side you will get a lesser force because of the presence of. There are rodless cylinders. There are what are known as rodless cylinders. More expensive. They are more expensive. Essentially, the cylinder will be something like this. There is a cut here. Take a tube, cut it along the length, slit it. Okay? That's okay. Now the piston is kept here, and something projects out of the piston through the slit, and that's the one that's moving up and down. And there are, along this length, in order to seal the air in, there are flaps which close like this, magnetic, and seal the air or whatever. These are rodless cylinders. Mostly it is used in pneumatics. So there is no piston sticking out. The whole thing moves this way and that way here. If something moves like this, no piston sticking out. Rodless cylinders. You can look up the web. You will see they will show you the pictures. Rodless cylinders. Many people use them, but there is a leakage here and all that. And those problems are there. Now, when you have a double acting cylinder and you would like to move it this way and that way, obviously you have to admit oil from one side to move this way, and then there are what are known as direction control valves. Essentially what they do is, if you have a valve like this and there is a solenoid, usually the solenoid will move the spool inside, so that when the oil which comes in goes either to this side or to this side. And remember, when you are moving like this, the oil inside on this side of the piston, supposing you are moving this way, the oil on this side of the piston has to be sent to the sump. All that is taken care of by the direction control valve, operated by solenoid. Then last time I had brought a few of those valves. They all look like that. It's a spool which moves up and down, connecting this port to this port. And okay. Now when you have pneumatics, I told you last time that the piston tends to go to the other end. The piston, once you have admitted air here, the piston tends to go to the other end. There is no control, I was saying. Just keep shooting off. As the air is admitted, usually they put what is known as a deceleration valve here. Deceleration valve. This is what it is. This is the one. The air on this side, you control the rate at which it is exiting and consequently decelerate. Okay, decelerate the piston. Instead of going and banging, decelerate. Sometimes there are external shock absorbers fitted here. Shock absorbers externally are fitted, spring and the dashboard. Sometimes they are also used. You may use a deceleration valve plus this, or no, pneumatics is quite fast, unlike it simply goes. But high speed also means that it will suddenly go and bang, and so you have to have these devices in order to, towards the end of the stroke, to control what you have. You have to have these devices. Deceleration valves, then shock absorbers, all these are used for now admitting air to these is through what are known as solenoid valves. If you are electrically actuating through digital control, switching these valves from, the valves which admit solenoids are used. Now, if you really want to have control on the flow, you have what are known as flow control valves. Now, there are shapers and there are machines where a tool reciprocates driven by a hydraulic cylinder. You can set the flow control valve to a specific speed and then you can have it reciprocating up and down. Okay. There are also what are known as servo valves. These are essentially flow control valves, but you can control the flow by a servo motor which drives the valve. Small torque motors they are called. Torque motor in the servo valve, a torque motor drives the spool, drives the valve, let us say, I should say, because there are so many valves, types of valves, there are spools, there are flappers and so many types of valves. Essentially what it does is, depending on the feedback from the cylinder, feedback control, the torque motor positions the flow control valve needle or spool or whatever it is so as to control it. Obviously, when you are doing such a control, you should have a very quick response. So you tend to use several devices, flappers, and so many things are there in order to control the flow. When the cylinder starts moving, you want to control, you have to accelerate, decelerate, all these things are done by this servo valves. Okay. Now, when you have a system of cylinders working, this is a typical, either both in pneumatics and hydraulics, it is a typical one. You have a machine where you have a number of pneumatic cylinders. This moves first. When that has completed, the next one moves. This is known as a sequencing. You have to sequence them in a particular fashion. Sequencing. Then there are several valves which are used. There is what is known as a pressure sequence valve. There are several. One is a pressure sequence valve. See, it is typically used like this. You have a job gripped. When the gripping force has reached an adequate force, when the gripping force is adequate to lift the job, that means the pressure in the cylinder must be of a particular value. At that value, the gripping force is adequate. You know that you have to grip it with so much force, so much pressure must be there in the cylinder. When that pressure is reached, only then will it allow the next cylinder which moves the job forward. See, you have gripped it. Now the next cylinder which moves the job forward must act. Wait till you grip, make sure the pressure in this cylinder is the right amount, and then only you let the next fellow go. That is what the pressure sequence valve is. You sense the pressure and then decide the next. Pressure sequence valve decides. Alternately, mostly what you have is solenoid operated valves. This is a special valve. Now let us say you are gripping an object. You can have a solenoid switching that particular cylinder which will go and grip the object, but you are not sure you have applied the right pressure. That is where this fellow comes in very useful, the pressure sequence valve. Until it touches the pressure, it won't allow subsequent operations to begin, the pressure sequence valve. Whereas the solenoid operated valves, you can sequence them. You have a set of cylinders, one moving in the x direction, another in the y direction. You want to move x first, followed by z, and then y, then solenoid operated valve. These are some of the valves which are used. Sometimes what they do is, instead of having a solenoid operating it, that means electric power is required to operate the solenoid, which in turn will operate the valve, which in turn. So that means the solenoid is directly driving the valve spool. So that what are known as, there are other valves, what is known as a pilot valve. For example, what you could do is, when the cylinder motion is completed, cylinder motion, here usually the word used is, you always think of the piston moving, but the terminology used by the industry is cylinder motion. It's a very peculiar. We have to, supposing this has hit this, then it might trip a limit switch, which in turn might, see, there is a air connection here to this limit switch. You have a pressure line, you have an air line going here, that you connect it to the limit switch also. When the limit switch is hit, this in turn will operate the actual valve, which in turn will operate the other cylinder, next cylinder. So these are the pilot valves. Instead of using a separate electrical connection to this you can, both are mounted together. That means instead of an electric solenoid opening the valve, you use pneumatic pressure to open the valve. So pneumatic logic is used in these cases. What you have is, just like you have this breadboard, you can connect the various valves on that. Using that pneumatic logic, you can sequence the way you want, send the signal to the corresponding valve, connect the valves through the pneumatic logic. So people use the so-called pneumatic logic is used. Then you can avoid the electric. Then in the case of hydraulic one, people have come out with fluidic logic. So, you have several technologies available for you as far as actuators are concerned. Several technologies. We have mostly looked at the basic electrical actuators. There are many more. It is endless, the amount of talking one can do about actuators. So I will summarize what we have seen in this particular lecture. We have looked at electric actuators in the last lecture and this lecture, particularly the stepper and servo. We looked at their performance characteristics, how to select them, what are the important considerations. We also have very briefly looked at what are known as pneumatic and hydraulic systems. It's a very simple view, and it will be useful to you as you go along. In the next lecture, I think we will be talking about sensors. We are looking at the various subsystems of the robot. We started with the main body, then we looked at the wrist, we looked at some math. Like that we have been going. So next we will see sensors, and then you will start looking at controls, kinematics and controls. That will be after we have finished this particular set of lectures on basic systems, subsystems of robotics. Okay, thank you very much.